Okay, let's talk some more about mineral stability and in different kinds of rocks like metaphylites and mafic rocks, and pressure, temperature, time paths. And I'll tell you a little bit about thermobarometry, and that is how we calculate the pressures and temperatures that a rock was metamorphosed at. All right, we've talked about politic sediments. These are mudstones and shales that are very fine-grained sediments that are derived from the continental crust. They accumulate on the parts of the wedge of sediment that's off the continental shelf or slope, the farther reaches of that wedge of sediment. And they grade into coarser greywackies, which is more a sandy sediment that's nearer the continental source, so closer to the edge of the continent. And while they're just muds, the metaphylites are an important family of metamorphic rocks because they're very sensitive to changes in temperature and pressure, and as you increase metamorphic grade in, for example, regional metamorphism. And they contain a lot of the diagnostic characteristic minerals that we can use to assess pressure temperature conditions in a rock. Okay, their metaphylites are dominated by aluminum and potassium-rich phyllosilicates like clays or white micas and chlorite. And those are all potentially the original detrital grains, so from the original sedimentary rock. And the phyllosilicates can comprise more than 50% of the original sediment of all those chlorite, the micas, and the clays. And then fine-grained quartz can make up another 10 to 30%. And those rocks may also have feldspars, some iron oxides or hydroxides, zeolites, carbonates, sulfides, and organic matter. Now, what makes metaphylites different from other protolith rocks is the high aluminum, potassium, and the low calcium. And that reflects the high clay and mica content in the original sediment and results in a lot of muscovite and quartz throughout most of the range of metamorphic grades, from low to high. There's a high proportion of micas, and you're commonly developing foliated rocks, such as those that we've been talking about, slates, phyllites, and mica schists. And the chemical composition of phylites can be represented basically by a system that contains potassium, iron, magnesium, aluminum, silica, and water. And iron and magnesium aren't making up a large proportion of those chemical components, but they're present. And we can abbreviate this chemical system as KF-MASH. Here's a phase diagram that you're familiar with already. And this shows you the stability fields for the aluminosilicates, common minerals that we see in metaphylites. And what you're essentially seeing is the Al2SiO5 is stable is stable in these polymorphs. So here's a phase diagram that you're already familiar with. And what this shows you are, for the polymorphs, the aluminosilicate polymorphs, the stability fields, those PT conditions where each of those polymorphs is stable. And as we've mentioned before, silimonite is stable at high temperatures, andalusite at low pressures, kyanite at high pressures. And as we increase the metamorphic grade in a rock, if we're talking about regional metamorphism, when we move from lower temperatures to higher temperatures, kyanite becomes no longer stable and sillimanite crystallizes in its place. It still contains the aluminum in the silica tetrahedra, but it's in a different crystallographic orientation, whereby sillimanite has a higher temperature structure. So you might imagine a more loose crystal structure, whereas a high pressure crystal structure for kyanite would be a denser crystal. That's one kind of transformation, a phase transformation from one phase to another during metamorphism, because one phase becomes stable in place of the former, what it's replacing. And the triple point between those polymorphs is at very specific conditions, at just below 4 kilobars or 0.4 GPAs and about 500 degrees Celsius. It would be a very rare occurrence to actually have those conditions and have kyanite, andalusite, and sillimanite crystallizing together in equilibrium. And it would also be equally unlikely to crystallize, to fall on those pressure temperature conditions right on that phase boundary where you'd be crystallizing sillimanite and kyanite at the same time together, or sillimanite and andalusite at the same time together. More likely, you're at some place in one of these stability fields in terms of pressures and temperatures, but you're crystallizing kyanite. And if you see both kyanite and sillimanite in a rock, what you're probably seeing is part of the pressure-temperature path. So the sillimanite crystallizing at lower pressures and temperature conditions than the kyanite crystallized at. Here's another kind of phase diagram. In this case, instead of being a phase transformation, there's a reaction taking place. And so we're going from, at higher pressures, jadeite and quartz are stable. Jadeite is a sodium-rich clinopyroxene. Jadeite and quartz are stable at high pressures, but at higher temperatures and somewhat lower pressures, albite becomes stable. So if your pressure-temperature path is taking you from higher pressures to higher temperatures, you're going to break down the jadeite and quartz to crystallize albite in their place. These are some examples of these solid state, they're called net transfer reactions, but essentially you're taking ions from some minerals and replacing those minerals and reorganizing those ions into a new mineral. So the example that I just used of jadeite plus quartz reacting to form albite, you'll see that the sodium and aluminum from the jadeite are combining with the silica in the quartz to form a sodium aluminum silicate, just a different one. And the reason the albite crystallizes at higher temperatures is because it, if you remember some chemistry, it has a lower Gibbs free energy at those conditions than do the jadeite and quartz. Another example might be enstatite and anorthite, anorthite being the calcium plagioclase. Those together can break down to form diopside and andalusite. So these formulas do balance, and you can count your ions here, but it all balances out. Another example would be hypersine and plagioclase breaking down to form a garnet, a clinopyroxene, let's say augite, and quartz. So these are sort of solid state reactions that are represented on a lot of phase diagrams that I'll show you more of in a minute. Another kind of reaction we might see is a devolatilization reaction, or dehydration is easier to say, isn't it? So a dehydration reaction if you're driving off water during a mineral reaction. And so here's an example of muscovite, and there's that hydroxyl group, plus quartz breaking down to form K-spar, sillimanite, and water. These are the kinds of reactions that I'm talking about when we're talking about dehydrating minerals, driving off the water, and the water then lowering melting temperatures of the surrounding rocks. This is the kind of this is one of those reactions. This is what a devolatilization reaction might look like. So you see a PT diagram with muscovite and quartz on the low temperature side, and on the high temperature side we see K-feldspar, the aluminosilicate, in this case sillimanite, and water. And this should make sense to you because at higher temperatures you don't expect the structural water to be stable in minerals. So all these dehydration reactions, you can anticipate that you have the hydrous phases on the lower temperature side and the anhydrous phases at the higher temperature side. So when we put a lot of these different things together, a lot of different stability fields and phase diagrams together, what you end up with are phase diagrams like this that represent many, many different mineral reactions in a pressure temperature space. And this one, believe it or not, is a relatively simple phase diagram. And it's simple because this is only representing a few chemical components. K-FASH and K-MASH are on here. So potassium, iron, aluminum, silica, and water, those phases are represented by the purple curves, and then the potassium, magnesium, aluminum, silica, and water are represented by the orange phase diagrams. Actually, I swapped that. K-FASH is the orange and K-MASH is the purple. Okay, well, what you see, let's just orient ourselves, and it's very handy that the kyanite, andalusite, sillimanite phase boundaries are there. That helps us kind of see what PT space we're in. And let me get rid of that so you can see more of the other reactions. You see reactions such as, here's a curve, which is chlorite and K-spar breaking down to form biotite and muscovite. Or at higher temperatures, we have biotite and quartz breaking down to crystallize an orthopyroxene like enstatite and K-feldspar. Or we might see the reaction between biotite and aluminosilicate, in that case it's a sillimanite, to crystallize garnet and cordierite. So this is simplified because we're only considering a few chemical components, not sodium, not calcium, not manganese, not titanium. So it's relatively simplified. And you'll just see that if, depending on what kind of rocks you're looking at, you're going to be looking at the reactions at high pressures and low temperature conditions. If you have a peelite that's being subducted and it's undergoing metamorphism in a subduction zone, or you might see a different set of minerals that are stable and a different set of metamorphic reactions for regional metamorphism at more moderate pressure and temperature conditions. Here's another system. This is slightly more complex because this is representing sodium, potassium, iron, magnesium, aluminum, silica, and water. And on this curve, we're actually seeing some dehydration reactions. So let's find, here's one, this curve here. I'll skip over the text so you can read it. We're seeing muscovite and albite breaking down to form an aluminosilicate plus a liquid, water. Now, those examples were appropriate for metamorphism of pilitic rocks. Remember that our components, that the chemical components that go into the metamorphism and the minerals that we crystallize are going to be different if we're metamorphosing mafic rocks. And this diagram is showing increasing grade for metamorphism of mafic rocks in particular. And what you should notice are more iron and magnesium and calcium bearing minerals showing up. So orthopyroxene, clinopyroxenes, calcium plagioclases, garnets, hornblends. So the assemblages that we get will look quite different. Here's a phase diagram for metamorphosed mafic rock that has a simplified chemistry of potassium, calcium, sodium, magnesium, aluminum, silica, and water, and a different set of minerals to go along with that. So in this case, we've got a lawsonite breaking down to form anorthite, the calcium plagioclase, quartz, and a fluid, or there's that quartz plus jadeite breaking down to form albite curve that we looked at earlier. Or here we've got prehnite plus chlorite plus quartz breaking down to form actinolite, epidote, and a fluid. So this is at low enough temperatures. This is only up to 700 degrees Celsius. If we look at slightly higher temperatures, we'll see more reactions come in. So let's expand the view to look at up to 1,000 degrees Celsius. This is the diagram we were just looking at over here. So that part of this pressure temperature field. And now we've added higher temperature conditions. And what do we see there? If you look just in these reactions, we see hornblende and plagioclase breaking down to form a clinopyroxene plus a fluid. So that is your dehydration reaction. You're breaking down the hornblende to grow the anhydrous pyroxene.